Hello and welcome to another episode of CSEC Math with Sarf Kumar. In today's episode, we're going to look at margin of error and scale drawing. We're going to define margin of error and we're going to look at some examples, and we're going to also define scale drawing, and we're going to use given scales to calculate actual distances on maps. The first thing we're going to look at is margin of error. Now, margin of error or measurement error is the difference between a measured quantity and its true value. It includes random errors, which are naturally occurring errors that are expected with any experiment, and systematic errors, which are caused by a miscalibrated instrument. Now, what does it mean by a measured quantity and its true value? For example, let's say you're going to buy steel rod, and you're going to purchase, let's say, a 10 feet length. Now, they're telling you that the length of this piece of steel is 10 feet. Now, the actual or the true value might be a little off. That is, it could be a little longer than 10 feet, or it could be a little shorter than 10 feet. And those are the little errors that we usually have in measurement. And these errors come by sometimes the random errors, which occur naturally, or the systematic error, which is caused by a miscalibration. So let's say the machinery that's cutting the steel, there was a slight miscalibration. So sometimes when you decide to say, okay, you know what, I have 10 feet here, but when you actually measure it, sometimes you come a bit short. So those little differences in measurement is what we call the margin of error. Let's look at an explanation of margin of error using a simple example. So let's say we have a length of steel rod to be 5.34 meters, accurate to the nearest 1/100 meter. Then the error interval involved in the length is plus or minus 0.005 meters. Now, how do we get this? It says here that the absolute error involved in the measurement is half of the smallest unit of length. Now, our error that we're working with is 1/100. So if we take 1/100, we're going to get 0.01 meters. And we're saying that the absolute error involved is half of the smallest unit. So 0.01 meters is the smallest unit we would have in the measurement. Therefore, half of 0.01 is going to give me 0.05. So this is the error when they say nearest to the 1/100 meter, then the absolute error that we're going to work with is 0.05. Now, let's go back to the length of steel. The length of steel is given as 5.34 meters. Now, our error is 0.005. The greatest length of the steel rod, so we usually say L max, which means the maximum length, and L max is equals to the actual length given, which is going to be 5.34 meters plus our error, which is going to be 0.005 meters, and that is going to give me 5.345 meters. And then you have here the least possible length of the steel rod. When you're finding the least possible length, we say L min, and L min is going to be the actual length, which is 5.34 meters, subtract our error, which is 0.005 meters, and that's going to give me 5.335 meters. Now, what does this mean? The maximum length that we could get from this steel rod would be 5.345 meters. And the least or the minimum length we could get is 5.335. So what we're saying is that when you purchase the steel at 5.34, possibility exists that the longest piece of steel you could receive is 5.345, and the shortest piece of steel you could receive is 5.335, given that we're working with an absolute error of 0.005, which is 1 over 100 meters. The first example in margin of error, the lengths of 3 rods were measured as 145.6 cm, 134.5 cm, and 125.7 cm, accurate to the nearest 1/10 cm. State the total length. So the first thing we have to find is the absolute error. So we're working with the nearest 1/10 of a cm. So this is going to be 1 over 10 cm. And when we divide here, we're going to get 0.1 cm. Remember that the absolute error is half of the smallest unit, so we have to now divide this by 2. So it's going to be 0.1 divided by 2, and that's going to give me plus or minus 0.05 cm. So this is the error we would be working with. So let's go and find the maximum length and the minimum length. So L max, remember we're working now with 1, 2, 3 lengths. So the first one is going to be 145.6 cm plus our error, which is going to be 0.05 cm. The second one is 134.5 cm plus our error, which is going to be 0.05 cm, and we have the last one is 125.7 cm plus our error, which is 0.05 cm. So let's add them. So 145.6 plus 0.05 is going to give me 145.65 cm. 134.5 plus 0.05 is going to give me 134.55 cm, and 127.5 plus 0.05 is going to give me 125.75 cm. So they want the total length. So in order to find the total maximum length, we have to sum the 3 pieces of steel as given. So adding 1, 2, 3, 145.65, 134.55, and 125.75, that's going to give me 406.35 cm. Now this value is our L max value. So this is the maximum total length for the 3 pieces of steel. Let's go and find the total minimum length. So we have L min, and I'm going to work down here. So now we're going to use the same 3 lengths, but this time we have to subtract our 0.05. So we have 145.6 cm subtract 0.05 cm. Then we have 134.5 cm subtract 0.05 cm, and then we have 125.7 cm subtract 0.05 cm. Subtracting them, 145.6 subtract 0.05 is going to give me 145.55 cm. 134.5 subtract 0.05 is going to give me 134.45 cm, and 125.7 subtract 0.05 is going to give me 125.65 cm. Now, to find the total minimum length, we now have to sum the 3. 145.55 plus 134.45 plus 125.65 is going to give me 405.60 cm. Now, we found the maximum length to be 406.35 and the minimum length to be 405.60. Therefore, we could say hence the maximum length is 406.35 cm and the minimum length is 405.60 cm. And this is what the margin of error does. So when the person purchased the 3 lengths of steel, possibility exists that the total length they could receive is 406.35 and the least they could receive is 405.60. And if we look here, we have the actual length. That is going to be the lengths that the person is going to purchase. The actual lengths, if we add them up, would have been 405.8 cm. So if you look at the minimum and the maximum length, you would see that this falls in the middle. The second example, the length and breadth of a rectangle were measured as 7.29 meters and 3.17 meters, accurate to the nearest 100th meter. State the area of the rectangle appropriate to the margin of error. So the first thing we have to do is find our absolute error. So we're working with 100th meter. So it's going to be 1 over 100. And when we divide that, we're going to get 0.01. Half of this is going to give me 0.01 divided by 2. And the error we're working with is plus or minus 0.005. Now, if you can recall from the steel rod example, the steel rod explanation, when we're working with 100ths, it's 0.005. And from the previous example, when we're working with 1/10, it's plus or minus 0.05. So this doesn't change. When you calculate here, it doesn't change. So if you could remember that 100th is 0.005 and 1/10 is 0.05, you don't have to do this step in every example. You could skip this and just state the absolute error and then you put this at the end instead of working all of this out. So let's go to the question. So we have to find the area of a rectangle. And if you could recall from our first episode, the area of a rectangle is equals to length times breadth. So they said that the length and breadth of a rectangle were measured as 7.29 and 3.17. So our length is equals to 7.29 meters and the breadth is equals to 3.17 meters. So let's go and calculate the area of this shape appropriate to the margin of error given. So the first thing we're going to do is to find the actual area of the shape. So the actual area, and that's going to be A is equals to length times breadth, and that's going to be 7.29 meters times 3.17 meters. So 7.29 meters times 3.17 meters. And that's going to give me 23.109 meters square. So this is the actual area of this shape. So let's see what the maximum area is going to be. So we say A max, and when we're working with the maximum, we have to add 0.05 to the length and the breadth. So our L max is going to equals to 7.29 meters plus our error, which is 0.005, 0.005, and this is going to give me 7.295, and the breadth max is going to be 3.17 plus the error, which is 0.005, and that's going to give me 3.175 meters. So now let's calculate the maximum area. So A max is equals to length times breadth, and that's going to be our maximum length, 7.295 meters, multiplied by our maximum breadth, and that's going to be 3.175 meters, and multiplying them I would get 23.161 meters squared. So this is the maximum area of this shape. So let's find what's the minimum area. So we say A min, but before we go and find the minimum area, we have to find the minimum length and the minimum breadth. So we say L min is equals to 7.29 meters minus our error, which is going to be 0.005, and this is going to give me 7.285 meters, and our minimum breadth is going to be 3.17, subtract 0.005 meters, and that's going to give me 3.165 meters. So now since we found the minimum length and the minimum breadth, let's find the minimum area. So A min is equals to length times breadth, and that is going to be 7.285 multiplied by 3.165, and our minimum area is going to be 23.057 meters. Now if you're to compare, sorry, it's meters square. So if you're to compare the three area that we have, the actual area, which is 23.109 meters square, the maximum area, which is 23.161 meters square, and the minimum area, which is 23.057, you could see that the actual area falls between the maximum and the minimum. Now they might look that it's a small deviation between the actual and the max and the actual and the minimum, but let's say the measurement is given as this precisely, and you have to fit this shape into an object. That's very important, and you end up with 23.161, therefore it would not fit. And similarly, if you end up with 23.057, it would be too small. So the margin of error is usually given so that you could make provisions for the differences. We're now going to look at scale drawing. So the definition: scale drawing is a model or replica that resembles the actual object, and the scale is defined as the ratio of a length on the drawing to the actual length of the object. Now, there are certain things that we cannot draw on paper. The actual size of the object we cannot put on a paper. So let's say the map of Guyana. We know that we cannot take pages and draw the actual size of Guyana. So what we do, we reduce the actual size to a given scale, then we use the scale to create a replica to resemble the map of Guyana. On your drawing on the paper, you're going to use measurements. So let's say you're going to say 1 cm represents 10,000 kilometers. So when you're looking at the map on the paper, you're already in your mind, you know that 1 cm on this page represents 10,000 kilometers. So that little ratio there, 1 cm to 10,000 kilometers, is what we call the scale. Now, when doing scale drawings, we have to use the units of measurement, and you have km, like kilometers, meters, centimeters, and millimeters. And you have to understand the conversion of these units. So if you're converting from kilometers to meters, you multiply by 1,000. If you're converting from meters to centimeters, you multiply by 100. And if you're converting from centimeters to millimeters, you multiply by 10. So when you're moving from a larger unit to a smaller unit, we multiply. So km to m, multiply by 1,000. Meters to centimeters, you multiply by 100. And cm to millimeters, you multiply by 10. And if you're going from a smaller unit to a larger unit, we usually divide. So from millimeters to centimeters, we divide by 10. Centimeters to meters, we divide by 100. And from meters to kilometers, we divide by 1,000. So remember this conversion table, because we're going to use this conversion to solve the examples. Let's look at some examples. So the first example is determine the actual distance between Georgetown and Skeldon. We're going to use the map, and we're going to measure the distance between Georgetown and Skeldon. For the examples, we're going to use this map here. And if you notice at the bottom, we have 1 to 5 million. This is the scale that's given. It's in a ratio. So that means that 1 cm represents 5 million. And then across here, you see that they gave us kilometers. So after using the length on the map and the scale, we have to convert our units, that is centimeters, to kilometers. So we're going to now measure on the map the distance from Georgetown to Skeldon. So we identify that here is Georgetown and here is Skeldon. So using this point and this point, we're going to measure. So we start from 0, and then we place the ruler at the 2 dots. And if you notice that from Georgetown to Skeldon, where the dot is, it is 3, and the 1 here, so it's 3.1 centimeters. Having measured between Georgetown and Skeldon, we found that the length on the map is 3.1 centimeters. And the scale given at the bottom is 1 to 5 million cm. That means 1 cm represents 5 million centimeters. So since the length on the map is 3.1 cm, we can go and calculate the actual distance. So the actual distance is equals to 3.1 cm multiplied by 5 million. And 3.1 times 5 million is going to give me 15,500,000 centimeters. But we don't want our answer in centimeters, we want our answer in kilometers. So we have to convert centimeters to kilometers. And if you can remember from our little conversion, from cm to meters, we have to divide by 100, and from meters to kilometers, we have to divide by 1,000. So if we work from cm straight to km, it means that we're going to divide by 100 times 1,000, which is going to give me 100,000. So converting to kilometers, we would have 15,500,000 cm divided by 100,000 cm. And what we do, we just cancel out our zeros, and what we have is 155 kilometers. So the actual distance between Georgetown and Skeldon is 155 kilometers using the scale given. The second example is determine the actual distance between Georgetown and Port Kaituma. We're now going to use the map and we're going to measure the distance between Georgetown and Port Kaituma. The second example, now we have to measure from Georgetown to Port Kaituma. So we already identified that here is Georgetown, and if you look, here is going to be Port Kaituma, so we're using the dot there. So let's measure. So we put our ruler at 0 to Georgetown, and then we go to Port Kaituma, and if you notice that it is 4.5, 6, 7, 8, 9, so it's 4.9. So the distance from Georgetown to Port Kaituma on the map is 4.9 centimeters. So from the map, we found that the length is 4.9 cm. And having found the length as 4.9 cm, we have to use our scale to find the actual distance. So what we're going to do is multiply the length on the map by the scale, and that's going to be 4.9 cm multiplied by our scale, which is 5 million cm. So 4.9 times 5 million is going to give me 24,500,000 cm. Now we have to convert our centimeters to kilometers, and from our first example, just remember that we're dividing by 100,000. So the conversion is going to be 24,500,000, 24,500,000 cm divided by 100,000 cm, and we cancel out our zeros, and what we have is 245 kilometers. So the actual distance between Georgetown and Port Kaituma is 245 kilometers. The third example, determine the actual distance between Georgetown and Christiansburg. We're now going to use the map and measure the distance between Georgetown and Christiansburg. We have to measure the distance between Georgetown and Christiansburg. So we know that Georgetown is up here and Christiansburg is here. So we have to use that black dot there. So let's measure. So we put 0 at Georgetown. And then if you look here, you could see it's before 2. So it's 1, 1.5, 6, 7, 8, 9. So from Georgetown to Christiansburg, it's 1.9 centimeters on the map. Having measured the length on the map, we found the length to be 1.9 centimeters. Now to find the actual distance, again, we have to multiply the length on the map by our scale, and that's going to be 1.9 cm multiplied by our scale, which is 5 million, and 1.9 times 5 million is going to give me 9,500,000 cm. Now we have to convert this cm to kilometers, and from all the examples, we divide by 100,000. So our conversion is going to equal to 9,500,000 cm. So it's 9,500,000 divided by 100,000, and we start canceling out the zeros, and what we're left with is 95 kilometers. So the actual distance between Georgetown and Christiansburg is 95 kilometers. In today's lesson, we looked at margin of error and scale drawing. We used the absolute errors to calculate the maximum and minimum lengths of given objects, and we looked at some steel rod, and we looked at area and and use margin of error to find the maximum area and the minimum area, and compare that with the actual area or the actual length of the objects. And in scale drawing, we use the map of Guyana and we use the given scale to calculate the actual distances between given locations or given areas in Guyana. So we looked at Georgetown and Skeldon, we looked at Georgetown and Port Kaituma, and we looked at Georgetown and Christiansburg.